Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
So the plastic zone size for a plane strain cases becomes finally Rp is equal to 2 delta is equal to 1 by 3 pi into K1 by sigma ys whole square. Okay. And then we can look at the another model, which is a very important model, because this model assumes the entire length of the plastic zone as a crack length. So this is what we are going to see. So this is called elastic analysis, and this schematic is shown here. What is proposed by Dugdale for this crack tip plastic zone, and what people have actually observed in experiments is this. The schematic is shown here. Okay. So this kind of analysis is suitable for thin plates, exact for materials responding to Tresca yield criterion, and plastic deformation concentrates in a line, also termed as strip yield model. So these are all some of the salient features connected to this Dugdale model, and then we will see how it is being carried forward. So this is a central crack in an infinite plate subjected to uniaxial loading. The crack length is now you see that 2a, and this plastic zone is delta and delta. So you have 2 delta plus 2a. Okay. So what is shown here? So though this is plate is subjected to uniaxial tension here, this particular zone, plastic zone at the tips, the two tips are subjected to some compression by the plastic, sigma x, sigma yx, that type of stress is acting in the opposite direction to the far field stress. Okay, so we will see how to handle this. Dugdale considered the effective crack of length a plus delta, where delta is the length of the plastic zone determined such that k sigma plus k delta is equal to 0. So how do we understand this? K sigma is a, this is related to the crack tip singularity, and k delta is, it is opposite, the cohesive force, which is compressed by the magnitude of sigma yx by this model. We'll see this animation again. K sigma is, we know that is sigma into pi a plus delta. K delta is a singularity due to the pressure sigma ys. So I'm saying it's a compression, so it is considered as a pressure. How do we carry this forward? So K delta from Green's function approach. So we will see what is that. So the Green's function, what is given here is basically the incremental crack plastic zone, crack growth in the plastic zone is considered as a ds, and this portion is taken as s, and then the dk delta is given by this expression, and then for this this is done. This expression is for the incremental growth ds. So if you integrate to the entire length, then you will get the k delta. So that is the idea. But if you look at this expression, it is minus 2 pi because of it is under the compression. So this basically, this expression, this k expression is taken from the wedge type of loading proposed by Westergaard's stress function. This expression was derived. Okay, we did not see it in detail, but you can go and refer in the textbooks. And the same, the wedge type of loading, at the two ends, the wedge type of loading type, the Westergaard stress function is given, and then the stress intensity factor is derived like this for the tensile load, but here it is a negative sign because of it's a compression load. So this is considered like a wedge type of loading, and which reads like that, sigma ys into ds into pi into a plus delta divided by square root of a plus delta whole square minus s square. So now if you can integrate this, so we have already done this kind of integration in the previous sections. So if you look at that, and if you look at the table of integrals, you will find the answer for this. So we are not getting into the details. Just if you look at all the steps, like some of the steps are skipped here, just applying the limits, and then you will get the final expression is like this. So from there, now we will proceed. You can rewrite this expressions like this form, where sigma into square root of pi into a plus delta minus 2 sigma y into pi into a plus delta by pi times cos inverse a by a plus delta is equal to 0. If you take out all this pi into square root of pi into a plus delta, then you can recast this equation like this. Since this is equal to 0, then this can be knocked off, and then you can get this expression. From this expression, you can rewrite this expression like this: a by a plus delta will be equal to cos into pi sigma divided by 2 sigma ys. So this is one final expression you get. So from there, you have to solve for the delta. So how do we do that? So that is what we are going to see now. An approximate but simpler relation may be obtained for the cases where sigma is far less than sigma ys. So this is something we have to remember. See, the sigma, when you consider this, then always the sigma which is appearing in this kind of an equation is much smaller as compared to the yield stress of the material. So, and this assumption is valid because it will give a good approximate estimate of this plastic zone. So then again you consider that delta is far less than a, and then you can rewrite that expression like that: 1 minus delta by a is equal to 1 minus pi square sigma square by 8 sigma y square. So then we get an expression for a delta like this, which is pi by 8 into k1 divided by sigma ys whole square. So now we can use this and then try to estimate through the experiments. Hahn and Rosenfeld demonstrated the existence of plastic zone as postulated by the Dugdale model. They used 3% silicon steel for the specimen, and the surface of the test pieces were electropolished and etched. So the method of etching ensured preferential attack of individual dislocation. This resulted in gradual darkening of the surface as the strain is increased from 1 or 2%. Okay. Beyond 2% strain, the etching response has diminished, and above 5% strain, no attack at all. So this is some kind of verification done by Hahn and Rosenthal about the Dugdale model. So the etching technique thus revealed both the extent of plastic zone and to some degree the distribution of strain within the zone. So the redistribution of the load is also being witnessed by the experiments. To reveal the plastic zone at various depths, the specimen is reground to various depths, polished and re-etched. Plastic zone shape of surface and midsection of sample specimen are as follows. So what is obtained by this Hahn and Rosenthal is given here. So this is very, very important. What is seen here is the surface. What you are seeing is the surface, and this is a side view. Okay, so it's very interesting to note that whatever is whatever the model proposed by the Dugdale, it is exactly resembling the same. The midsection plastic zone resembles the shape of the plastic zone predicted by Dugdale model. That is very important. So now let us look at the summary of the plastic zone lengths. For a simplistic model, we had for a plane stress and a plane strain model is this, we have already seen. And Irwin model is given by these expressions, and then a Dugdale model gives only for a plane stress situation, not the plane strain situation. Just to recall what all the plastic zone size we are able to appreciate. And what about the correction in the crack length? That is also a simplistic model gives considered as an RP in both cases, plane stress and plane strain. Irwin model gives the RP by 2, the crack tip at the center of the plastic zone. In both the cases, it is approximately RP by 2, and Dugdale model again considers the as an RP. Okay. So now what we will do is we will try to classify them. Classification of a plane stress and plane strain based on the plastic zone size. How do we classify based on the plastic zone size? If delta is less than B by A, then that is belong to plane strain condition. If the delta is greater than 4, B by A is the plane stress condition. So this is one important idea to keep in mind. So how do we know estimation of minimum thickness of the fracture toughness test specimen? So if you want to, this is going to be a huge challenge. What is the minimum thickness for estimating the fracture toughness of the test specimen? For an experimental determination of K1C, the material plane strain condition is assured by taking the specimen thickness to be much larger than the plastic zone size. This is the first point. Specimen thickness is recommended to be more than 25 times of plastic zone size. That means B should be greater than or equal to 25 into 1 by 3 pi K1C divided by sigma ys whole square. That is, B should be greater than 2.5 into K1C by sigma y whole square. So in order to take the valid K1C test, this is the first primary conditions. The sample thickness has to be of this order. So this we will see when we do the fracture toughness testing. We will look at all these conditions much more closely. So how do we estimate the stress intensity factor considering the plastic zone size? Using the Irwin's model, especially in the plane stress condition. The corrected stress intensity factor of an infinite plate is given by this. K1 is equal to sigma pi into A plus delta to the power half. Though K1 is based on the effective crack length, A effective for an infinite plate, a closed form expression is possible as given by this models. K1 is equal to sigma pi to the power half into A plus K1 square divided by 2 pi sigma ys square whole to the power half. You will get sigma into root pi A plus sigma into square root of pi K1 divided by square root of 2 into square root of pi into sigma ys. So this is one way of getting the K1 with the plastic zone. So finally we will get this. K1 is equal to sigma into pi A divided by 1 minus 1 by 2 into sigma divided by sigma ys whole square whole to the power half. So this is one very important expressions for stress intensity factor. Correction in the stress intensity factor finite plate. So we know that now so far we have looked at infinite plate and we will now come to finite plate. Since K1 is based on effective crack length A effective, in general it has to be determined iteratively, and K1 is equal to sigma pi into A plus delta to the power half. Then we bring in the A by W factor. So this we have already seen. You are not new to this. It's a function of A Instead of A by W, it is A plus delta by W. So now you get the expression, final expression like this. K1 is equal to sigma pi to the power half into A plus K1 square divided by 2 pi sigma ys square into, as a function of A plus, we have this expression for delta K1 square divided by 2 pi sigma ys square divided by W. So this completes the, the stress intensity factor for a finite plate. So we will solve some numerical examples later. Then you will get the impression of the plastic zone on, or the influence of plastic zone on the stress intensity factor. So now there are some iterative procedures to evaluate the K1. So I'm not going to spend time on this. So we will take it up later. So now, what is important point to note here is variation of plastic zone shape over the thickness of the specimen. How do we visualize this shape? The shape of the plastic zone is not same over the thickness of the specimen. A variation exists. An approximate variation can be obtained as follows. The surface of the specimen is ready to contract and the plastic zone shape can be approximated to be as that for the plane stress case at the surface. In the interior of the specimen, the shape can be approximated to be that for the plane strain case. This is what we have seen in the selection of fracture toughness slide. Okay. If no redistribution of loading is considered, the variation of the plastic zone is given as this schematic. So this is very interesting schematic. You see that the specimen thickness is shown here as a B, and this is a cracked up. This is at the surface, which is a plane stress condition, and this is inside this thickness, which is a plane strain condition. You can see that this is the magnified view is given here. These are all slip surfaces, and this is called butterfly plastic zone. This also mode 1 isochromatics are similar to this. And if the redistribution is calculated and then again this plotted like this schematically, though it does not give much difference between the redistribution after the redistribution, but nevertheless it gives the idea, the original idea into the same, where the plastic zone size will be bigger on the surface, that is a plane stress condition, and in the interior it will be a little larger, and which will represent the plane strain condition. Okay. So now another important point is influence of plastic deformation on the nature of the fracture. Okay. At low stress levels, one observes a hinge type of plastic zone. At high stress level, the plastic zone is projected in front of the crack in the direction parallel to the crack plane. So look at this animation. So this is the kind of plastic zone region is demonstrated, but it is also experimentally observed by Hahn and Rosenthal, which we have already just seen in the previous slide. So we will now get the details how we can understand this. So slip plane in the plane strain, you can see that it is a maximum shear, plane of maximum shear, and then the crack tip region is shown here. How the slip takes place. So the slip takes place like this. It is sliding in each other. Each region is sliding over each other. In that process, the crack extends by tearing. So that is what is shown here in the schematic. And then what happens when slightly interior the plastic zone? It is quite different now. You see that the plane of maximum shear stress is something similar to what we have already seen. It is it is these type of 45-degree planes, which is not in the same plane of the axis, stress axis, but you can see that how the 45-degree plane moves in this zone. Okay, that's how the plastic zone develops. So this is some nice schematic which gives a visual impact of how the crack tip stresses or crack tip plastic zone evolves. Okay, so this is slip planes in the plane stress, again the plane of maximum shear, and yeah, and this particularly we have already seen this in the introduction, one of the introduction slide. So what you are seeing here is the plastic zone, from the crack tip it goes like this, the crack grows in the plastic zone, and finally it fails by the shear lip. Okay, this is something which we have to remember. Okay, so what I will do is I'm just rushing through because I just want to give you an overall flavor. But my intention is not to dump too much of information, but at the same time my concern is the materials students also should have all these ideas to in their mind when they compare the fracture mechanics problems. Then it is easy for you to understand the general literature, and then you can be understand all the languages talked by the full community. That's my intention. Okay, so I will stop here, and then we will continue in the next lecture on the another topic in fracture mechanics. Thank you.